Swayam Prabha. Digital India. Educated India.
So, in the previous lectures, we had been looking at ways of deriving the equation of motion of continuous systems. So, we derived equation of motion, the boundary conditions, and we also looked at initial conditions which close the system. That means, we will then have unique solutions of our system. Now, so this part we derived those equations by two ways. One was a Newtonian approach, the other was a variational approach. Now, in the next few lectures, what we are going to do is analyze these equations or solve these equations. So, the first thing that we note is that we have the equation of motion, then we have the boundary conditions, and we have the initial conditions. So, this is what we have in hand. Now, what can we do with these? So, in the general situation, what we can do is, given these three things, we can solve the system. We can find out the solution, we can find out the behavior of the system. But then with change in initial conditions, for example, the solution will change. Now, if the solution changes, then we are not able to get a feel of the system. So, the question that we put is whether we can find out some characteristic solution of the system. So, what we are interested in is finding out certain characteristic solutions of the system. By characteristic solutions, I mean that things that will not change, the solutions will not change, that those things will not change with change in initial conditions, or certain properties of the system that will not change with change in initial conditions. So, from so can we find such characteristic solutions? So, the answer to this question is an affirmative, and we know this from our study of vibrations of discrete systems. So, in there we solve for what are known as the natural frequencies of the system. Natural frequencies, so how fast the system is going to vibrate. So, that is, I mean, an idea of that is given by the natural frequencies of the system. By natural, we mean that the system is in free motion, it is not being forced or disturbed from outside as such. The other is how the mode of vibration. So, one thing is the natural frequencies and the corresponding modes of vibration of the system. So, these two constitute the characteristic solutions of the system, and finding them out is known as modal analysis. So, when we do modal analysis, what we are doing is actually searching for solutions of very special form. So, if you recall the equation of motion of a string. So, suppose it is a fixed string, of length L. So, we have the equation of motion and the boundary conditions. Now, our field variable is this w x comma t. Now, this is a general function of the spatial coordinate x and the temporal coordinate t. Now, when we do modal analysis, we are searching for solutions which are of a very special form, which look like this, where this I is the square root of -1, omega is known as the circular frequency, and w is the amplitude function. So, we are searching for solutions of this very special structure, in which in a certain way the spatial function and the temporal function are somewhat separated. Now, they look separated, but remember that we have introduced. So, now this solution is in the complex form. So, this w may in general be a complex function. In that case, the solution is not strictly separated or separated in space and time, but we will encounter such solutions later in this course. So, for the time being, we introduce this complex solution structure, and we say that the actual solution, because our equation and the boundary conditions are all real. So, the actual solution is obtained by taking either the real part. So, the actual solution will be obtained by taking either the real part of this quantity or the imaginary part of this quantity, or a linear combination of the real and imaginary parts. So, if you consider this possibility, and we will initially most of the systems that we are going to study will have this capital W, the amplitude function, as real. In that case, we can rewrite this solution in the form So, if you consider that w is a real function, and as I mentioned that you can take the linear combination of the real and imaginary parts of this complex solution form as the general solution, then your solution looks like this. Now, from this structure we can deduce immediately a few properties of this solution. So, here you can immediately see that the solution is strictly separable in space and time. So, space part and the time part, they are separated. Then this, the temporal part of the solution can become 0 at a certain time instant. In that event, all points for all x, the solution is 0, which means that the motion of the string or the continuous system passes through the equilibrium point, all points pass through the equilibrium point at the same time. So, the system passes through the equilibrium point. So, all points of the system pass through the equilibrium point at the same time instant. Then there are points, there can be points at which W x is 0. Such points are called nodes. So, there is a possibility of existence of nodes where W x is 0. The fourth property of this solution structure is that the phase difference between any two points of the system is either 0 or pi. So, if you take any two points x 1 and x 2, and if you observe the product of this amplitude function, if this is positive, then the phase difference is 0, if it is negative, the phase difference is pi. There is another interesting property of the solution, that is the ratio of amplitudes at x 1 and x 2 that is independent of time. That is to say, this ratio. So, essentially this is independent of time, as we can see. So, we will start with this structure of the solution and see or try to find out the characteristic motion of the system. So, to do this, we will start with the example of the uniform taut string. So, the equation of motion and the boundary conditions look like this. Now, we are going to substitute this solution structure, and if you do that and with a little rearrangement, you can easily see the equation reduces to this, because exponential I omega t will never be 0 for any time. So, the remaining part, the coefficient of exponential I omega t, which is this, must be 0, and along with this we must have the conditions at x equal to 0 and x equal to L. Now, this differential equation is very familiar and the solution can be written directly. Now, this is the general form of solution of this differential equation. Along with this, now we have these boundary conditions at x equal to 0 and x equal to L. So, we will substitute these in the boundary, this solution form in the boundary conditions, and we can rewrite the boundary conditions in this form. Now, if you want to have non-trivial solutions of D and H, which is what we desire, then the determinant of this matrix must vanish. So, that implies so determinant of this is nothing but sin omega L over C, and that must be 0. This equation is known as the characteristic equation. Because it yields, this condition yields certain characteristic solutions or properties of the system, and they are the circular frequencies, which are also known as the natural frequencies, circular natural frequencies of the system. So, from this condition we can immediately write that omega, now there are discrete solutions of this characteristic equations, but there are infinitely many of them. So, there are countably infinite many points at which this will be satisfied for special values of omega. So, we will put an index n and write this as where n, this index n, goes from 1 to infinity. So, there are countably infinitely many natural frequencies of a string, of a fixed string, which are given by these values. They are called the circular natural frequency also sometimes known as the characteristic frequencies. Of the system. Now, once we find these special values of omega in this matrix for which we have non trivial solutions, then we can really find those non trivial solutions by finding the corresponding d and h values, which look like so if you substitute these values of omega n into the boundary conditions, now it can be easily seen that the solutions are or can be written in this form. So, anything proportional to this will be a solution, where again n goes from. So, corresponding to each circular natural frequency, you have this vector which gives you the actual solution, which is obtained as these are called the modes of vibration, or they are actually the eigen functions and again they correspond to the natural frequencies of the system. So, for every natural frequency there is an eigen function which defines or describes a mode of vibration. So, the total solution now looks like so everywhere we have this index n. So, here also I must have this index n. So, this is the solution for each n I can have a solution, and since our system is linear, a superposition or a summation of this solution is also a solution. So, I can finally sum all these solutions and construct the most general solution of a vibrating string with fixed support. Now, this structure looks very familiar if you think of the Fourier sine series. So, this represents a function which is periodic, and so the periodicity is L. So, L is the where L here refers to the length of the string. So, this structure of the solution finally what we have is like a Fourier sine series. So, which means that any shape of the string, since we know from Fourier series theory that any shape between two supports if I have this shape, by continuation I can construct the Fourier or represent this as a Fourier series, Fourier sine series like this. So, any shape of the string is now at any time instant, if you think about the shape of the string at any time instant, then this is a constant which is represented here as a n, and then this is expanded in terms of these functions sin n pi x over L. Now, we also know from Fourier series theory that these form the basis functions which are orthogonal, in the sense that so, if you integrate, perform this integration. So, if you take any two eigen functions with different index n and m, multiply them and integrate from 0 to L the length of the string, then it is L over 2 the Kronecker delta m n. So, which means if m is not equal to n, this is 0, if m equal to n, this is L by 2. So, these are orthogonal. So, sin pi x over L is orthogonal to sin 2 pi x over L, etc. So, if I make a graphical representation of this solution, I can think about it with a slight stretch of imagination. Suppose I draw axes which are orthogonal to represent this orthogonality conditions, and I call it sin pi x over L, call this axis as sin 2 pi x over L, etc. I cannot draw all these infinitely many axes, but I appeal to your imagination that you can consider this to be an infinite dimensional space where axes are orthogonal to represent the orthogonality of these functions, and then a solution of this form or a representation in this form for a particular shape of the string is actually a point in this infinite dimensional space. This is A1, this is A2, this is A3, and like this you can have all these coefficients A1, A2, A3, A4 up to A infinity. So, in this space the configuration of the string at a time instant, at a particular time instant, is nothing but a point in this infinite dimensional space. So, as the string moves, so it is nothing but the motion of this point. So, if the string executes a periodic motion in this space, then it would be a perfectly a closed curve. Now, in this space then, what is the simplest motion that is possible? So, the simplest motion would be, for example, the string moving only along this axis, only along this axis. This is a modal solution, the motion of the string in the first mode of vibration. So, this motion is nothing but only sin pi x over L, is represented by sin pi x over L. All the other coefficients are 0, A2, A3 etc. are all 0 except A1. So, this is the first mode of vibration of the string, which looks like Similarly, if you consider motion only along the second axis sin 2 pi x over L, then the motion of the string looks like this. So, essentially the string is vibrating between these two extreme configurations, and the corresponding frequencies corresponding circular natural frequencies are given by these values, omega 1 as pi c over L and omega 2 as 2 pi c over L. This infinite dimensional space is sometimes called the modal space. Or sometimes also can be called the configuration space of the string. So, in this space the configuration of a string at any time instant is represented by a point, and it is nothing but when it moves from one configuration to the other, it is nothing but the motion of this point in this space. And we have seen that the elemental motion or the motion along these axes, they represent the modal solution. Now, I am going to demonstrate with a small experiment these solutions, but before that let me just point out here that as you can see in this solution there is no node within the domain of the string, whereas here there is one node. Where the string remains fixed. This point is not moving out from the equilibrium position, whereas other points are vibrating. Here all points are vibrating in the same phase. So, the string essentially moves through intermediate configurations like this and then again comes back and passes through the equilibrium point. So, at the equilibrium point the string again becomes straight and then starts moving down and reaches this extreme, again repeats, starts afresh. Here the intermediate configurations look like this. So, you see a point here and a point here, they are simply out of phase. So, when this is moving up, this is moving down and vice versa. So, but 2 points on this in this lobe, they are moving in phase. So, either the phase is either 0, phase difference between 2 points of the string is either 0 or it is pi. So, now I will demonstrate using a small experiment these modes. So, here I have a string which I have made taut by pulling, and here there is an exciter which is nothing but a simple electric shaver. Now, as I pluck the string, you see the motion ceases after some time. This is expected since all real systems they have internal damping, but in our model that we have considered till now we do not have damping. So, to cancel the effect of damping I must have an exciter which must pump the same amount of energy that is being dissipated with the due to the internal damping in the string. Now, let us see. So, this is the first mode of vibration of the string. This is how it will look like when it is vibrating in the first mode. Now, let me try the second mode. So, this is the second mode of vibration of the string, and I may also try the third mode which may not be visible very clearly because the amplitudes are so small, but the second mode is quite clear and the first mode as well. So, this is what we have observed. We have seen the first two modes quite clearly, third mode because the amplitudes are so small has been is less visible and so on for the higher modes. But then whenever I pluck a string, I actually excite a number of these modes. So, the motion of the string, if I pluck a string at an arbitrary point, then I am actually exciting a number of these modes. So, the solution is more complicated, but I can by special means excite only these individual modes, and we have seen that in a demonstration. The next example that we are going to look at is that of a uniform hanging chain. We have derived the equation of motion of a uniform hanging chain previously, and it looks like So, this is the equation of motion, this is the boundary condition at the fixed end, Now, once again we are going to attempt a solution with this structure, and we obtain with the boundary conditions Now, in the case of a string of a uniform taut string, we obtained the equation previously. After substituting the solution structure, we obtained a differential equation and boundary conditions. Here again we have obtained a differential equation and boundary conditions. This problem is known as the eigenvalue problem. So, in the case of a string, this was our eigenvalue problem. Now, this structure of equation looks tantalizingly familiar, because we have studied equations of this structure when we discuss Sturm-Liouville problems in mathematics. Now, to convert this, because this is a particular I mean this structure is very special, we can convert this into more familiar, into a more familiar form by using transformation of the independent variable x. So, let us consider a variable s which is a function of x if you use this new variable s, then you can replace which you can check very easily, where w tilde is a function of this new variable s, and similarly you can work out the higher derivative. Now, having done this, if you substitute back in the equation and convert this equation in terms of s, then what you obtain is with the boundary conditions this can be checked very easily. Now, this is a very familiar equation which is the Bessel differential equation. So, this equation is the Bessel differential equation, and if in this equation if you put n as 0, then it reduces to this differential equation, and the solution of the Bessel differential equation with n equal to 0, which is the solution for our w tilde, where j 0 and y 0 they are known as the 0th order Bessel function of the first and second kinds respectively. Now, if you look at these Bessel's functions of 0th order, then you will find that this second kind has a logarithmic singularity at s equal to 0. So, if I make an approximate plot of J 0, so at s equal to 0, y is minus infinity. So, this will violate this condition, this boundary condition, which is the boundary condition at the free end. So, finiteness of the solution at the free end forces us to select E as 0. So, E must be 0. So, therefore, which can be written. So, I can write this down in terms of my original variable x, but before I do that, let me look at the boundary condition. So, we know that this implies this must be 0. Now, you can see from this figure there are finite number of points, but infinitely many there are discrete points, but infinitely many at which this function j 0 is 0. So, these countably infinitely many solutions of this will give us the natural frequency, circular natural frequency of the system. And if I represent this by something like gamma k, then this gamma 1 is approximately 2.4048, gamma 2 is 5.5201, gamma 3 is 8.6537, and like this you can find out the values, and from here, from these values of gamma k, therefore, you can find out, say for example, you can easily write omega 1 as 1.2024 under root L over G. So, you can see that compared to a mathematical pendulum, this is 1.2 times higher. Now, finally, once you have this, you can write the general solution. Once again using superposition, where, so these represent the modes, these are the eigen functions, and the modes of vibration of a uniform hanging string are defined by these eigen functions. So, the modes of vibration of a hanging string are defined by these eigen functions, and they look So, this is the first mode. This is the second mode. And this represents the third mode. Now, once again I will demonstrate to you the modes of vibration of a hanging chain. So, if you see this chain, so this is the first mode of vibration. Now, I will try the second mode. So, this is the second mode of vibration of the chain. Exciting the higher modes is little more difficult. So, in this lecture what we have studied is the modal analysis of continuous systems. So, we started off with a modal analysis of a taut string, and then we looked at the properties of these modal solutions, and finally, we also looked at the example of a uniform hanging chain. So, with this we come to an end of this lecture.